So we are going to review the important parts of our material, and then today we're going to talk about the surface code and up to green theorem. Okay, so let's first define our line integral. So we have line integral, surface integral. Each line and surface integral has two different types of integral. One is integration of function of real value, and the other is integration of vector field. So whenever we have integration of real valued function, I'm going to write just f without the arrows on top. And the notation of line integral is this, just one thing, but it has all the information. We're talking about the curve, talking about the function, and ds is just meaning that we are integrating over the line segment, small s, and this is defined to be fct c prime t dt. Okay. So here's some information missing because where is AB come from? It's the start and end points of the interval of the parameterization of C. And what is CT? It's the parameterization. And what is C prime T? It's the vector, the tangent velocity vector of the point moving along this parameterization. And T is the time. And we're talking about the value of function at the point on the curve. So at the time t, the point is at ct, so we are taking the value at that point. So another one is, so it's clear, it's just single variable integration. So another one is about surface integral. So we have the notation as follow. We have double integration because it's surface, because it's two-dimensional. We have two s's here. And it's defined to be integration over some rectangular domain or D, whatever. So let's say A, B, C, D, F, S, U, V times S, U times S, V, du, dv. So we have a double integration. And the integrand is the value of function at the point on the surface and multiplying the size of a cross product. So I explained why we need to multiply this because we are so what is UV? UV is the parameter which lies on the UV plane on the rectangular domain, and we are not looking at the surface on UV plane. Surface is on the XYZ space. So we want to integrate on the surface, but the actual calculation is done on the UV plane. So we have to modify our UV plane's area to the surface area, the small surface area corresponding to the small rectangle on the UV plane. So that's the one we need to multiply. We need a modifying factor to adjust our UV plane small rate area to the actual area on the surface. So in some sense, it's same idea as the Jacobian. When we had an integration by substitution on the double integration, we need to multiply the Jacobian. And this is the same idea why we need multiply Jacobian. So that's one thing. And then let's see. So when you have a vector field, you can take a line integration along the curve where the curve is parameterized in a certain direction. Then it's written as this. So we have f arrow, meaning that it's a vector field. And to indicate that this is the line integral of vector field, we have ds arrow. And this is inner product notation, not the multiple notation. And the definition is f c t, which is a vector, inner product c prime t dt. So again, this is the more single variable integration because this is just the number and t is the only parameter we have in the integration. And our parameterization is same as the line integration above, but the meaning of here is different. Here, what we are doing here is we have a value at the point and we are multiplying the small line segment of the curve to get the line times the value, which kind of meaning the area. So we talked about the meaning of the line integration as the area under the graph of a function over the line. So it's kind of an area of a kind of curved surface. But here we are taking an inner product between two vectors. So the vector F is a vector field. So you can imagine that this is the physical field, force field. And then we're take an inner product with C prime. So it's the instant velocity. So when you take an inner product between the vector field or force field to the velocity vector, you're calculating the actual work done to the direction of your movement. So in some sense, and also you need to multiply dt to make actual distance unit here. So you want to take how much your point ct is moved in a small amount of time dt, and with a direction, and then you multiply the force applied to that point or object, and then calculate the small amount of work done by the vector field to move a point from one point to another in a small amount of time. So you're kind of taking all the sum of small work to get the entire work to make the object move from one point to another. So this is the work done by the vector field on the point along the curve CT. So it's quite different meaning here. But you can see that mathematically, the line integration of a function and a vector field is just boiled down to the single integration here, single variable function integration. And in the surface case, so this is the surface integration of the function of real value. But let me define the integration of a vector field today. So let's say we have a vector field f x, y, z, a, x, y, z, b, x, y, z. Let me say PQR. I think I used that PQR in my book. Instead of A, B, say PQ, R, X, Y, Z. So this is three-dimensional vector field, and PQR is the formula of three coordinates of my three-dimensional vector. And I want to take the surface integral, so I need a surface. Let's say this is my surface on three-dimensional space, and this is parameterized by two variables. So let's say this surface, it's kind of sitting above the UV plane on the bottom here. So let's say UV here. So U is from A to B, V is from C to D. And then I have a one-to-one mapping from one point on the rectangular region to the point on the surface of three dimension. And this is defined to be the integration over A, B, C, D, so far the same, F. So here the parameterization of the surface is a small s, S, U, V here, and inner product with n, so I'll define n what that is, times, so n and S, U cross S, V, du, dv. So n, so let me explain it before I explain what n is. So here I have three-dimensional vector coming from the vector field f. And then I have another three-dimensional vector called n. So in fact, this n is also vector field. Okay, so basically two vectors, two three-dimensional vectors, merge inner product together to get the real number. And we have the same factor we had in the surface integral of a real valued function. So basically, this is the definition. And what is n? N is the orientation, and it's defined to be SU, SV, SU, SV. What does that mean? So it's a cross product divided by some value, the real number. So basically, it's a unit vector because it's divided by its size. And when you take the cross product, you know that this new vector is perpendicular to both of the three-dimensional vector that is product together. So it's kind of perpendicular to the direction, to the plane, perpendicular to the plane, which is parallel to SU and SV. And this is called the orientation of S. But let me explain, I'll explain what the geometric meaning of this, but before, let me put this back in here, our formula, to simplify our formula here. So this is A, B, C, D, F, S, U, V, inner product. So when you have N instead of this, when you have N replaced by this, then you have a canceling of this size. You get S, U plus S, V, D, U, D, V. So you can work with either of this. You can just memorize this as definition or that. Okay. So let's think about orientation. Let's think about the meaning of this cross product with an example. So here we have a sphere, and we know how to parameterize our sphere. Let's say our sphere has a radius 1. So the obvious one is the spherical coordinate system. So we have R is a rho, the radius is 1, so we only need theta and phi. So when I have point on the sphere, then the theta is the angle between the z-axis and the line joining the origin to the point on the surface. And when you take a projection onto this xy plane, so there is an angle that makes between the positive x-axis and the projected line here. I'll call it phi. So in mathematics, in many mathematics texts, they change the uses of these symbols, theta and phi, in other way. But this is the common use of this theta and phi in physics settings. So I'm going to stick with this. So how do you, first of all, what's the range of theta and phi? So theta range from 0 to pi to go to the south pole here. So it's a pi. And phi is round up one circle here. So it's 2 pi. So this is the rectangular domain that maps to the sphere almost one-to-one fashion. Almost. There are places where you don't get the one-to-one mapping. When theta is 0, you are at the positive x-axis. When theta is also, theta, not theta, phi is 0, then you're at x-axis. But if your phi becomes 2 pi, you go back, you round once, and then you're at the same x-axis, right? So you get a 2-to-1 map between this line, 0 and 2 pi. But that's okay, because when we take this parameterization, spherical coordinate system, we mostly talk about the surface integral, and surface integral is about multiplying the surface area, and we are not having the one-to-one mapping on one line of the surface, this line, right? And this is not equator, what is it? So it's kind of an altitude, right? Longitude, right? Longitudinal line, and the line has no area, right? So even if we don't have one-to-one map on this line, the surface integral doesn't change. So we can just keep this some exception on this line, and then do the computation. So anyway, what we want to talk about is, let's say if I have a point inside of this rectangular region, maybe identified as this point on the surface, and I want to look at what this SU and SV is. So in this case, S is the mapping, and instead of using U and V, I use the theta and phi. So what is S theta here? So S theta, so don't try to write down the formula, just think about the meaning. So this is a partial differential of S. Partial differential means that I want to see the instant rate of change by changing one parameter, theta, but keeping the phi, another parameter, the constant. So I want to keep the phi constant. So I'm moving along this line, but I want to move the theta, change the theta to the positive direction by 1 unit of length, right? I want to make a change of this point to this direction. So think about the actual trajectory of the point. If point on this rectangular box is moving along this line, so it's changing the theta, meaning that theta is increasing, so it will keep the phi, the longitude, but changing the longitude, latitude, yeah, it keeps the longitude but changes the latitude, right? So it's moving along this line, that longitudinal line. I forgot, it's just confusing. So anyway, this line, right? So this line. So instantly, as it moves just about this point, it will move along this tangent line, tangent direction, right? So it's not really moving in that tangent line, but it's moving in that direction. So if I just looking at the direction, then this direction, the vector, is actually tangent to the surface. So this is your SU, S theta here. Okay. So how about SV? So V is phi. So if I move along this phi line, by keeping theta, I'm moving upward. So phi is increasing. So phi is the angle between this positive x-axis to the counterclockwise direction. So if I fix my theta, it's moving along this circular rim here. So it's moving in this direction. So SV is this vector. Okay. So now we have S theta and S phi. Let's take a cross product between these two, S phi. What is it? So again, if you take the cross product of two three-dimensional vector, it's another three-dimensional vector that is perpendicular to both of these three-dimensional vectors. It must be some vector pointing outward from the sphere. Why? Well, because I took the cross product in this order, S theta and S phi. So if you think about the right-hand rule, that the cross product has a direction of a thumb when your forefinger is moving from theta to phi direction. So let's say my forefinger is moving from theta, S theta and S phi direction, then my thumb is pointing up here. So it's pointing outward to the sphere. And it's perpendicular to both of this three-dimensional vector. So this three-dimensional vector is actually tangent to the surface of the sphere, right? So if you span your vector, you will get the plane which is tangent to the sphere. So your cross product is actually tangent to the surface, and it's outward. So that's what this means. This means this. And how about this? What is the orientation? So you had this vector, and you multiply or divide it out by the length, which means that you keep the direction, but you want to normalize the size. So normalizing size means that you don't want to think about the size anymore. You just want to think about the direction. All you care about is the direction. So let's say I normalize the size, just keep the direction, and this is my n. What I'm doing here is I'm inner product the normalized direction to the vector field. So let's say our vector field is, let's say, pointing this direction at this point. So let's say, let me draw this picture again here. So n is here, and f is this direction. So this is three-dimensional vector, so keep that in mind. And what does fn mean? If I take the inner product between f and n, what does that mean? So this f vector has a component which is parallel to n direction, right? If you decompose your vector, three-dimensional vector, into three different components, let's say three perpendicular components, and let one of the component to be parallel to n, then your f inner product n is the component, the size of the component that is parallel to n. So in other words, if you take a light and shade, put your lights on the perpendicular direction to the vector n, then the shade is made to the direction of n, and the length of the shade is going to be exactly fn, and this vector will be this much long times this direction. Okay? So you're looking at how much the component, how much is the work done to the direction of your unit vector n. So that is what is going on. This is what's going on. Now, again, even though I said it's a work done, or maybe it's not work, because we're looking at the surface integral. And what do you mean by work done on the surface? Well, it doesn't really mean anything, so it's not really it's not really intuitive to think of that way. So let's think about this as a flow of a vector field, kind of a liquid flowing out of the surface, or air or whatever that flows is coming out from the surface. Okay, so when you say that this is when you see this kind of situation, your F is representing the vector that flows, the direction of the flow. This vector indicates that at each point, the liquid or whatever fluid is flowing in that direction. And what you're talking about by taking inner product is you want to measure the exact amount of flow, exact amount of liquid that is flowing outward from that surface. Because here is your surface. If the liquid is flowing along the boundary of the surface, then it's not going out, right? It's staying on inside, okay? It's not even inside. It's just doing nothing. It's not giving you any information about whether the liquid is flowing out or in. So you want to measure exactly how much is going out. So if it's out, then it's going to be positive to the direction of n. If it's negative, it actually flows in. Okay, so whatever that is, you don't want to measure that is the current of water that is flowing on the surface, right? You want to go for the exact amount that is flowing out, right? So this is the amount of flow, amount of water or liquid that is coming out, flowing out from the surface. So basically, what we have here is the rate of flow to the direction n. I should put the word direction n because it depends on which direction am I looking at. So suppose that the water is flowing out of the surface. If I want to measure water actually going out, then it's going to be positive, right? Because it's going out. But if my perspective is how much is getting in while the water is actually going out, then my value will be negative because it's actually going out, but I want to see how much is going in. So I need to take the value negative. It's minus 100 going out, meaning that it's 100 going in at the same time, right? So it's the rate of flow to the direction of n. And I also want to multiply this factor, which is the area of the small area of a surface. So what am I looking? So I have a rate of change of the flow, which is the velocity unit, right? Meter per second to the direction of n. And I multiply it to the area unit, which is meter square. So what's the unit overall? Meter per second times the meter square is the meter cube per second. So it measures how much the volume of the flow or liquid is going out to the direction of n per second. It's called a flux. So if you multiply these two, it's called flux. Again, flux is how much the liquid or fluid is going out to the certain direction at each time. So it's rate of change of the volume of a fluid over the time along the certain direction of the surface. So let me write this again. So just summarize, complete our list here. So F vector field ds and A, B, C, D, F, S, U, V, inner product, SU, SV, DU, DV. So we're going to look at the example, but before, any question? No? Just think about a few seconds. So by the way, how is the project going on? So don't forget there is a project presentation at the end of the semester, and there is a final exam schedule announced maybe last week. So on Monday, I think we're gonna have a presentation, and Wednesday we're gonna have a test, paper-based test. And frankly, I haven't graded the midterm test yet, but I hope that the test is straightforward. The last time it was very straightforward, right? So, yeah, I will grade before the end of the semester. So, and then you probably want to see the feedback, right? So the type of the question on the final exam will be similar to the midterm exam. And in the presentation, I understand if you're not familiar to the coding, then you probably want to try to explain the background on this project in more detail. So don't be too stressed out about making a code or making a visualization of the code. Just present whatever you understand from the project. And also, if you're doing the project too, the Ig Nobel Prize type, then also just try to think about your idea and how to present that idea in a logical way, instead of trying to spend too much time on writing the code. Okay, so let's look at example. A simple example here. Let's move this a bit here. Okay, so we have x, y, z. So our vector field is just x, y, z. Okay. So meaning that it's a three-dimensional. So if I have, let's say, x, y, z, then it's moving in the direction of x, y, z. Okay, a simple vector field. And our surface is sphere of radius 1. Here's one question. Is it enough to compute our surface integral of a vector field? Is these two information enough to get the flux? So it was enough if we had a surface integral of a vector, a real valued function. But we are talking about integration of a vector field. It's not enough. We need one more piece of information, which is the orientation of surface. We need the orientation. Why? Because there's no unique orientation. There are always two orientation. So look at the surface. This is our surface, right? It's a sphere. What is one orientation? Let's say the outward is one orientation, right? You want to see, so what is the orientation? It's the basis where you can say it's inside and outside. Okay, so basically you want to see which part is outside, which part is inside. Here, the outside, because we said the outward is this direction, the outside is the outside of the sphere. And inside, okay, it's the opposite of the outward, it's the inside of the sphere. But you can see this opposite way. See, if you looking at the orientation to be inward, so you're looking at inward, then the inside of the sphere is the outside, and outside of the sphere is the inside. So let's say people living on the Earth is pointing their heads up to the sky. So that's why we have the outside of the sphere is the space. But let's say there is another, let's say, there's a science fiction movie that the people are living inside of the sphere of the Earth, that is inside of the hull of the Earth, that they're probably looking at the inside of their heads are up to the core of this sphere. Or their perspective, their inside is the inside of this globe, the sphere, right? The outside is the outside of this. Outside is inside, and inside is outside, right? So you need the orientation. You need to choose among these two orientations, which orientation are you talking about? Which is the outward that you want to measure your flux of your vector field? So whenever you want to compute the surface, the information has to be given. Let's say is the outward of S. Let's say outward to be intuitively the outward, actual outward of sphere. So what is it? So outward of the sphere, and also has to be the perpendicular to the surface of sphere, and it has to be the unit length, unit vector. What do you think that is? So again, this orientation is a vector field because the outward direction, which is perpendicular to the surface, is always changing its direction, right? You cannot say this direction is the outward orientation because it's not perpendicular to the surface. So it has to be this direction. So it's changing the direction at every point of the surface. So in some sense, this orientation is the same as our vector field definition. It's an assignment of three-dimensional vector at every point on the surface. So now let's look at this orientation in coordinate. So let's say x, y, z is the point on the sphere. And how do you describe the x coordinates of this vector, n? Here we have origin on the center of the sphere. You have a point x, y, z, and you want to point out the perpendicular direction of your sphere. What is the coordinate? It's x, y, z. Why? Because x, y, z is on the sphere of radius 1. So if you connect the point origin to the point, this arrow is of length 1, and you can just translate this arrow all the way up to the point to start from here, and then this is exactly the perpendicular arrow from starting at this point and has the length 1, right? So this is my outward direction, the orientation. So orientation is also x, y, z, right? So let's take them here. So what do we have? So I can have one more step here. So we had orientation n, and we have s, right? So ds arrow is actually the orientation times ds, because the size of ds is the size of the small area of the surface, and it has a direction, which is the orientation of surface. So you can split ds arrow into n arrow times ds. So this fn now inner product to what? We have f, we have n. Now let's put this back here. X squared y squared plus z squared ds. What is this? X, y, z is lying on the unit sphere. So therefore, x squared, y squared, z squared equal to 1. It's 1. So what we are doing in this setting is just simply integrating 1 over the surface. What does that mean? So it's going back to our integration of real valued function. Our real valued function is just 1, which is constant function, and we are integrating over the surface. We said that this is the mass, which is the mass of the surface, where the f is the point density, right? Here our point density is 1. So let's ignore the unit here. So if the mass of density is 1, then mass is exactly equal as a value to the area of the surface, right? So what is the area of a surface, the unit sphere of radius 1? 4 pi. So we have 4 pi, okay? So I chose this example because it's easy to compute. We actually nothing to compute here. But we also don't forget to give a meaning to this value. What does this mean? This 4 pi is the flux of a vector field given here to the outward direction of the sphere. Okay, because we defined our orientation to be the outward. So it's the amount of fluid coming out from the surface of sphere at each second. So in some sense, in each unit of time, this much 4 pi amount of fluid is coming out to the direction of from the surface. Okay. So this will be explained again when we talk about Stokes theorems and divergence theorem later. But just summarize again. So the one important thing is that every time you compute, so here I think, let me summarize these two. So every time you compute integral of vector field, either line integral or surface integral, you can remember that you can always make it back to the line and surface integral of a real valued function. So here you can say that this is f times, let's see, n ds, and this is f times, or let's say this is n, not n, let's say v, because I don't want to confuse you here. So fn d large S. Here our v is the unit vector along the direction of movement along the curve, and this n is the orientation, SU SV over SU SV. Okay. So here, again, let me explain the meaning. We are talking about the amount of work done along the curve, because this is the force. This is the actual force applied to the direction of movement. Okay? This is the force times the length. ds is the length unit. Because if we were 1, just we're taking a small amount of length segment and then sum them up to get the entire length of a curve. So this is force times length, which is the work done on a small length unit ds, and then we sum them up to get the entire work done by the vector field. And here we're taking a flux, I mean kind of current, velocity, the velocity current, and then multiply with the area unit, the small area. So this is how much the water or fluid is coming out in direction of n through the surface, and then you multiply the area to get the actual flux. It's the total, it's the volume of the fluid coming out from that surface to the direction of n over time. You sum them up to get the total flux. Okay, so just remember these two identity. Maybe if you, even if you forget everything, just remember this and also the meaning. Then, even if you don't, so if you remember the core idea, I mean, you may forget the formula, but if you remember the core idea, you can always come back and then recollect all what you have memorized or you understand before, and then you don't have to get lost every time. Okay, so let me look at another example. Also, and let me explain very important notation of our integration here. So there are two different ways of writing the integral of a vector field. One is like this, which is the mathematical notation. And in physics, they use different notation. What is that? So let's say our vector field is, so this is a map. So it's, let's say, xy is sent to pxy and qxy. Okay. So whenever I have this situation, I'm going to omit x comma y because it's obvious that we're talking about the vector field is defined on xy plane. Or we could say xy z equal to pxyz, qxyz, and rxyz, if it's a three-dimensional vector field. So instead of writing this long notation, I'm going to just put f equals to pq. And in this case, I'm going to write just f equals to pq r. Okay, just understand that whenever I write this, that x, y, or x, y, z are omitted here. So in this case, the line integral is written as p dx q dy over c. So if it's two-dimensional, or if it's three-dimensional, you can also write the three-dimensional vector field, line integral of three-dimensional vector field, p dx q dy r dz. Okay. So why is this? Why is this useful? I mean, there are two questions. How can you write this? Why do you write this? And why is this useful? So think about this situation here. Let me erase this above. So when you have your f to be PQ, and let's say our CT is XT and YT, then your line integral is PQ, line integral of FC prime T dt. You can write that out as PQ inner product x prime y prime dt, right? So and then let's take the inner product. So it's over C, px prime plus qy prime dt. And let's put dt on every component, dt. So and then x prime dt and y prime dt seems like it's dx dy. Why? Because x prime is dx over dt, y prime is dy over dt. So you can replace this dx and dy. So therefore, you can say p dx and q dy. So why is this useful? It's a very intuitive way of what's going on. So look at this curve, and let's look at the p dx. And it's added with a q dy, so you can actually write this out in this way, p dx plus q dy. You can separate your integral. So in fact, actually, you're not separating an integral. You're actually separating your vector field, p0 plus 0q. But anyway, so what does that mean? So if you look at this first part, let's think about this way with an example. Let's say this is my origin, 1, 1, x and y, and we have the movement of the points along the boundary of the rectangular region here, square region, and this is my C, and my vector field is x squared, y squared. Okay, so I want to compute the line integration of this vector field. Okay, so let's try to just use this, rewrite this line integral in this notation. What is it? So it's integration of p, which is x squared dx, plus integration of q dy, right? And it seems like I can do this integration separately, and you can. Let's see. So what is the integration of x squared over dx? What does that mean? So it's not familiar to us to have no bound here when you take the integration in x. Instead, we have curve, which lies in two dimensions. So it means that we are moving along the curve, but we only observe the changes in the x coordinate. So dx is basically changes in your x position, right? Dx is a small increment of x position, x coordinate. So look at this curve. Let's say it doesn't matter where you start. Let's say it starts at the origin, and it's going to the right, up, left, bottom. And if you're going up or down, is there any change in x coordinates? No, you don't change it. So all you need to observe is how to get the integral, how to get the sum of x squared when you move along from this to the right or to the left up here. So if I split this curve into 4 pieces, let's say this is C1, C2, C3, and C4, along the curve line C2 and C4, there's no dx. Dx is 0. So it's going to be automatically 0. So all we need is just integrate over c1 and c3. So this is c1 x dx and c3 x dx. Okay? How about c1? Now, we need to parameterize. We need to do formal, if you really want the formal calculation, then you have to parameterize c1 and so on. But think about this way. When you move along c1, y is not changed. Y is always 0. Your x is changing. So you just concentrate on what changes. So all you need to observe is the x-coordinate along the c1. So x-coordinate is the parameter which changes from 0 to 1, and you're integrating x squared dx, right? And how about c3? So that's a c1. And you get the c1 by taking integration like this, which is just simple integration. And how about c3? You're moving from 1 to 0. Now you also want to concentrate just what is changing. Y is not changing. Y is always 1, right? But the value 1 is not reflected here because there's no variable y. So all we need to do is just take a x change from 1 to 0. So it's changing from 1 to 0 of x squared dx. So what is it? If you add them to integration, what is it? 0. Yeah, it's 0. Can you guess what this second integration could be? Yeah, it's 0, 2. Yeah, same. So you want to go for C2 direction and C4 direction. So you're still moving along C1, C3 on this part, but it's not going to be any value because dy is 0. So, and it's a coincidence that you have a same integration but different order of your boundary so that it cancels out to 0. So it's anyway, it's a 0. So that's one way you can think about your line integral in a different perspective. You only want to measure the changes of your x-coordinate and y-coordinate and see how it sums up to some value here. So again, let me introduce another notation for surface integral. So this is not really common notation that you might find in any other calculus textbook, but I think it's very important to understand later understand the Stokes theorems and Green theorems or divergence theorem later. So let's think about f ds, where your vector field is p, q, r. Then this is same as r dx dy. I need to be careful about this. So r dx dy plus, let's see, p, so let's see, xy, yz is x. So p, y, z, q, z, x. Okay, so sorry for having this. Okay, so you can rewrite your surface integral in this way. And I'll explain why I keep this order. So xy, yz, and zx later. For now, let's consider this is just the same, the symbol that we had in the double integration. So just dx dy is one unit, one thing here, and dy dz is just one thing. So why is this useful? So let's also think about this situation similar to this, that our surface is very flat, but has several components. Let's say we have this box, rectangular square box here. We have 1, 1, 1, and z here, x and y. And let's say our f is let's see, 1, 1, 1. Let's make let's make it here. So x, y, z. Okay, so to make it simple, but not too simple. And I want to say my surface is not entire surface of this cube, but there are three parts, only the three parts that you can see right in front. So we have S consists of S1, S2, and S3 here. Three parts, only the three parts. So now, this is not a closed surface. The closed surface means that there is no boundary. What's the boundary? Well, it's the end, the tip of the surface. The sphere has no boundary because there's no tip. It's always going in a circle. But here, we have a boundary of a surface, which is the rim here, right here. Because we're not covering entire boundary of the cube. We only see these three pieces. So the inside of these edges, it's not boundary, it's just the corner, right? It's still connected to another surface. But on these boundary, on this rim, there's no way you can go more, right? So it's boundary. Now, still you can find the orientation. You can still see where is the outside, where is the inside, because you can see, you can separate the space into outside and the inside. So let's say our outside or orientation to be the outward. So outward. So it's outward, which means that it also perpendicular to every part of the surface. So in the top part, S1, it's pointing out upward, and S2, it is upward, out this word, and S3, you get the out rightward here. I want to integrate, I want to find out the surface integral of f of this surface with this orientation. So how do I do that? So let's go for this. Let's go for this notation. And you can rewrite this as, also in this case, it seems like you can separate your integral into three double integration. This one, this one, this one. So let's rewrite in a separate way. So first of all, z or r part is z here. So z, that's not it. Okay, so this z. Oh. Z and dx dy plus what? P is x d what was it? Y d z, and q was r y d z dx. Okay, so let's try to compute this part first. So what does that mean? So I'm looking at the entire surface, but I also look at the small increment of x and y. I only want to look at how much the increase of x and y, the sum is b. So we have S1, S2, and S3. Look at S2. Is there any changes in x coordinate in any point in x2? No, because the value of x coordinate is always the same. Dx is same. Dx is always 0. So how about S3? dy is 0 because there's no change in y coordinate. So even if you have to integrate over S1, S2, S3, the integration over S2 and S3 will be automatically 0 because the dx or dy equals to 0. There was no area. So in some sense, you're looking at the projection image of this surface onto xy plane when you do this, because you only want to see the xy changes, not even the changes of z. We don't care about the changes of z. You're looking at the point from above to the xy plane and then see how it moves along xy plane. So that's S1, right? So this one, is S1 z dx dy. And it's quite straightforward because on S1, what is the value of z? 1, right? So it's a 1 dx dy over S1. So what we are looking at is the projected area of S1 onto xy plane, which is 1, right? And how about this? So you're looking at yz. The only thing you get the yz is non-zero is S2. So you want S2 x dy dz, and what is the value of x? It's 1. S2 dy dz, and it's 1, right? And then S3, and what we have is y dz dx, and it's 1. Sum them up to get 1, 3. So it doesn't have to be always like this, which is flat. Let's say we have some irregular shape. Let's say it has kind of this figure here, and this is my surface. And also, let's say this is my vector field f, and also there is a orientation of the surface outward. And let's say I want to integrate s, this f over s along this the orientation. And you can also do this the same way we did here, that it's r dx dy and so on. So there are 2 more, but just concentrate on here. What does that mean? I want to look at the integration of r in dx dy. So which means that I want to look at this surface from top to the xy plane. So which means I want to just look at the image of the projected image of this surface, and then see how this r changes as I move my point xy inside of this shaded region, and then sum them up at all points in S. But the question is, so here it's not one-to-one mapping. So I made this figure so that it's kind of a 2-to-1 mapping here. So there is a cut here. So if I cut through this line, then the bottom part of the sphere has a 1-to-1 mapping to this shade, and the upper part also has 1-to-1 mapping. So what I have to do is, in this case, I need to separate these 2 parts in 2 pieces and integrate in a different way, so in a separate way. So first of all, integrate over S1 and integrate over S2 in 2 different ways. Okay, so just make sure that nothing confused about this. So now here, the reason why I just need S1 is because I don't have the bottom part included in my surface. Only S1 has 1-to-1 correspondence with the area of projected area of xy plane. So I'll get here again when I explain Stokes theorem later, probably next time or next week. But any questions about this? Because first reason is because it has different orientation. First of all, the orientation on the S2 is this direction, and S1 is the opposite direction. Okay, so let me, a good question, so let me explain again. So let's say we kind of see the section area, a section figure of this, and let me separate these S2 and S1 in this way. So here we have a same shadow of S1 and S2. And same shadow means that this domain D is the common domain of the parameterization of S1 and S2. So D from S2 and D from S1, from D to S1 and S2 has 2 different parameterization, right? Because 2 different surfaces. And now the problem is we had an orientation which is defined on this closed surface. The orientation on S1 is here in this direction, and S2 we have orientation in this direction. So let's say our D lies on UV plane, and S2, S1 and S2 lies in XYZ plane. So if you want to get this N, let's say N1, you need to, let's say, take S1U cross S1V divided by the same thing here, if you want to go upward orientation, right? Because if you have a point here, and this is your U direction, and this is your V direction, and it corresponds to this point, and U direction movement changes to a point here, so this might be your S1U, and V direction change will be S1V here. So if you want to go upward, then you have to take a cross product order to be S1U times S1V. But however, what if I have here? So if I have UV moving in these 2 directions, then U direction movement is maybe S2U in this direction, And v direction movement is somehow, let's say, this direction as v direction here. That makes sense? As sorry, so the v direction, this v direction, so it should be the opposite direction, the s to v here, right? So it's kind of going backward here. Okay. So if I want this to be my orientation, then you shouldn't take S2U times S2V, because if I take the forefinger in that order, then my thumb is pointing inside of my surface. So instead, I need to get SUV times S2U to get this direction, right? To get the right hand rule here. So N2 is S2V times S2U and divided by the size. So I'm explaining why we need to take this case separately, because we need a two different way of defining my orientation. We cannot use the same parameterization for both surface. So if we are taking one parameterization to cover both of this surface, both of this part of surface, then we're fine, we're okay. But in this setting, we're automatically looking at these pieces of surface as if they were the projection from the shaded area of this XY plane to the part of that surface. So we are already defined our parameterization as the projection parameterization here. So in that case, we have to separate these two as a separate integral to make two different orientation. So that's why. So let me say this one. So let's say here is an example. Again, let's assume x, y, z. We have all six sides of the cube, okay? So the entire closed surface S. And I want to integrate x squared, y squared, and z squared over the S. So how do I do that? So maybe, okay, so better one would be, let's see, I want to make it better. So that's plus 1 here, because I don't want it to be 0. X squared, y squared, z squared plus 1. So again, let's split them up into 3 pieces like this. So let's look at the first pieces. So we have z squared plus 1, which is r times dx dy, and plus something, but I'll do it later. But here, what I care is top and bottom part. Let's call top part S1 and bottom part S2. So S1 z squared plus 1 dx dy plus S2 z squared plus 1 dx dy. Can I do this? So here, what I have in the top part is I have orientation outward. So let's suppose that orientation is always outward of this cubic surface. It's going outward. So yes, I can take dx dy in this order, because this order actually represents the order of cross product. So I can just take the area of the small area on xy plane, which is represented as dx dy, and then multiply z squared plus 1 to get the entire integral. So that is 1, so it's going to be 2 always. So it's the integration of 2, the real number 2, over this S1 shaded area, the projected area of S1, which is just 1 by 1 square. So it's going to be just 2. And how about this? So now in S2, orientation is not upward, we are going downward. So what we really need is the negative of this to get the right orientation. If we add if you just take the integration of this and just add them up, then what I'm actually doing here is I'm taking an orientation, the same direction of the orientation on S1, which means this. But I don't want that. I mean, the surface is the closed surface, the entire cubic surface. So my orientation on S2 is opposite, so I want to integrate how much is going out from this direction. So I need to get minus, because if I just take this dx dy, which means that it's just area, and multiply z squared plus 1, z squared plus 1 is how much is this vector field has the z coordinate, and this basically gives you the flow, direction of flow, but I want to measure the amount of flow in this direction. So basically, what's going on here is 0, 0, z squared plus 1 integral inner product 0, 0 minus 1, which is the orientation on S2 and dx dy. So therefore, I need a minus of z squared plus 1. So in this case, it's minus 1. Right? Just make a calculation in your head. Z is 0, so it's minus 1 integration over the 1 by 1 square, so it's minus 1. So that's why you have to separate out two pieces if they are not one-to-one in the projection. Well, it depends on what orientation that you're looking at is. And so actually what happens is, in that case, you have to write down dy dx in this case. So overall, what this happens is you get z squared plus 1 dy dx, meaning that you're looking at your xy plane in a mirror image, not xy orientation, but yx orientation. It's kind of mirror image. So in this case, if you really want to be peculiar about this writing, then so only for this case, your integration on S of r dx dy could be S1 r dx dy plus S1, sorry, not S1, it's S2 and the y dx. So I'll explain more about this notation later when we get to the Stokes theorem, because in physics, I'm not sure whether physics take this notation seriously, but in mathematics there is a meaning to the order of this multiplication of d parts. It's called the differential form, and you can kind of extend the idea of vector field to the meaning of a form. So it's very interesting if you go deeper into this subject. But normally what happens in the calculus text or calculus curriculum is that they collect all the easy parts from the differential geometry and then put it into a kind of a problem that you can write, you can solve it by your hands. But if you really understand what's going on, this whole theory can be explained in one term, which is the differential form in this way. So that's why I'm trying to emphasize this, and I think it's more useful to have this notation than having this kind of settings in a real situation. Like if you're reading the paper in physics or in engineering, you might see that this notation more often than this one. So you need to understand what this means. All right, any other questions? So let's see, we have, okay, so let me let me introduce the Green theorem and maybe we call it a day. So for now, we're gonna talk about two-dimensional vector field. So the Green theorem states the following. So if you have a vector field whose x-coordinate is p and y-coordinate is q, and you take an integration along the line with a certain direction, which is closed curve, then this is same as the double integration of this real-valued function whose value is defined by qx minus py over the domain D, where domain D is the region bounded by this closed curve. So, and also, whenever you have a closed curve, you take the region bounded by the closed curve to be always the inward of your closed curve. So what I mean by inward is that if you move along the orientation of a curve, then the inward is the left-hand side of your side of your body. So let's say you're moving in this direction. Your left arm is pointing inward. So that's where your region D is. So notice that there is a circle around this symbol S, meaning that the curve S, a curve C, is closed curve. Closed curve means the starting point and end points are the same. Okay, so this is a green theorem. Let's try to prove this. So because I want to show you the use of this notation here. And if you look at the calculus textbook, maybe they don't use these settings here for the reason that they don't introduce this notation. But I like this notation because it's easy to remember the formula. So let's think about this domain D in a very specialized case here. So let's say we have x-axis here, and our curve consists of 4 parts. Let's say C1, C2, C3, C4. Okay? So the C4, C2, they are vertical line, basically. It could be very tiny or none if it's just a round circle. But let's say for generality, let's say C2, C4 is kind of a vertical edge around the boundary of this x range. And let's say I want to compute this part, the left-hand side. So let's try to compute the PDX around C here. So I'm going to separate out these 2 parts and then combine it later. So what is PDX around C? So I'm going to see DX part. So only part that is not 0 is when I'm moving along C1 and C3. So basically it's integration of along C1 and C3, right? So let's say I have kind of a function that has a graph exactly same as the boundary curve C1. So then let's say this is a graph of G1 and this is graph of G2. Okay, so and then let's say our x range from A to B. So what is C1 then? So I'm moving along this direction. So x is moving from A to B. And my y is determined by the value of x. So in P is a function of x and y. So y is G1x and x is x. And I'm taking dx, right? And then what about C3? So C3 is moving along here, graph of G2, but in backward. So starting from B to A, so B to A of P x, G2x dx, right? Make sense? So I'm using just notation of this line integral. And then let's combine this. So I need to match, I need to make it common starting and endpoints A, B. So it's going to be minus if I exchange A and B here. So it's going to be P x G1x or minus P x G2x dx. Okay, so how do I get this? Whoa, how do I get this? So you can imagine that this is something like you get something like this. So P x y, where y is from G2x to G1x. Like you get the antiderivative and plug back the numbers into your formula and dx. And think about how you get Px y and then try to plug in the value of y. This is similar situation that you have the Fubini theorem. So let's say you have the partial differential of P, and then you take integration, kind of partial integration in terms of y as if x is constant, and your bound is same as here, g2x to g1x. So, and then you take the integration of x from a to b, right? So if you just think about this iterated integral, the inner part is you take the antiderivative of py in terms of y, which get the p, right? Just opposite direction of integrating a part of the derivative. And then you multiply the bounds, plug in the bounds here, right? So, and then let's switch the bounds of this g1, g2, okay? So if you just change the order here, whenever you change the order, you get the minus, right? So minus of a, b, g1, g2, py, dy, dx. Now, let's use the Fubini theorem, real Fubini theorem. You get this formula from Fubini theorem when you take the integral over domain D, which is bounded by g1 and g2 of py dx dy. Right? So where we came from? So we came from the integration, line integration of p along the curve C, and we get that this is equal to minus of double integral of py dy dx. So you can put the minus inside, so it's minus py integration. So now you can do the same thing, similar thing to the second part. The second part, you can actually put the opposite direction here. So D looks like this. You have a flat boundary up top and bottom, and then you get this, so you get this integration over the curve q dy to be integration of dqx dx dy. So you get the sum them up. So on the left-hand side, you get the normal line integration. On the right-hand side, you get exactly this. Okay, so you might ask, okay, so D is different shape. How can I do that? Well, if it's the same shape, you can just separate it out into similar, different regions. Let's say this is your, whatever, weird region. It can be anything. I'm saying that the curve can be anything as long as it's closed. Then, if you want to find the equality, the first equality of this, then you go for whenever you have that shape. So take the vertical line whenever the curve is having a tangent line vertical. So here the vertical, let's say where? So vertical, here maybe vertical, right here. So how many regions do I have? So maybe I don't have to split this up into two. So D1, D2, D3, D4, D5. For every DI, you can prove that this line integral is same as the integration of D. And then you combine them up. So how do you combine? So at every, say this is the curves, there are boundary curves, C1, C2, and C3, and C4, and C5, D4, and C5. So every CI, your P dx equals to integration of di minus py dx dy. You sum them up. Okay? So on the right-hand side, it's basically sum up all the double integration on each region. So it's going to be the double integration of entire domain, D, right? So that's fine. So this is the integration over D of minus py dx dy. How about on the left-hand side? Now, there's something that you have to be careful about. So here, C1, look at C1. So C1 is the closed curve surrounding D1. So this here is going backward and here. So there is a portion that's going upward here. But this portion is common to the closed curve of C3. So C3 is going this way, all the way up, and then left to the bottom here. So this part is common to the C1 part. So C1 is going upward, while C3 is going downward. Okay? So what happens is you're integrating the same function or same vector field in two different ways. One is upward and the other is downward. So what happens when you go up and down, get to the original place? So you go up and down. So when you take a sum here, there is a portion of line integral that goes up. And then from when you take the integration of C1, And then you're going down when you take the integration along C3. So when you go up and down of the same vector field, you get nothing. The work is 0. The work done is 0. If you go whatever the place, you come back, nothing is done, right? So this part cancels out. So there is no line integration along this line after you sum up all this line integration on the left. All same here, same here, same here. So what is left is just the boundary curve. The work done on the boundary is only the thing that left. So on the here, so you get all the boundary curve, the line integration on the boundary here. Okay. So by doing this, you can show that these two are equal. On here, now you can do the same thing with a horizontal line. Just take a horizontal line whenever you have a flat tangent. Here we have here and maybe here. Okay, so maybe put it here. Yeah, maybe here. Yeah. So in that case, you can do the same thing, same idea that there is some common boundary, right? But it cancels out on the left-hand side. So when you get this identity on the left-hand side, the common boundary go forward and backward, cancels out, and it's actually same as this to get basically this identity here.